Okay, student, let's finalize this example to speed up your lab 2. For the relay 3, as the relay 2 operation time is 0.1, okay, discrimination time must be added to 0.19. Uh, Operation time for the relay 3 as a backup is a 0.19 plus discrimination time, which is 0.59, correct? 59, correct? Okay. Then we have to calculate the PSM for the backup fault. It means that we have to consider the fault current at the relay 2, which is 14,715 times by uh, CTR. The CTR here is 5 over 1100, correct? And then the PSM, sorry, the PS times the pickup current. Where is the pickup current? The pickup current is 8. Yes, given by 8 here. Okay, the pickup current. So the final value, if you calculate well, the final value here, it reached to 8.38. Okay, so this is the PSM backup and this is operating time. Let's find out the time deal setting for this relay. So for this relay time deal setting, start with 8.3, 8 point, this is 8.5, this is 8.4, correct? Okay. Then operation time is 5.5, 5.5, something roughly around here. If you zoom in, you can see it's look like at that point, at this point, correct? So you can check it better whether you choose this one or this one. So let's see which one we must choose. This one is 5 and the other one is 6. So I suggest to pick up 6 to make it a safe system for yourself and safe operating time. So you can see by here we also pick 6. For the other side of, because relay 3 is already, it's placed by here, okay? The other side of this relay, both relay is for the transformer, correct? So the fast operation of this time is mainly related to the transformer. So the transformer thermal limit means how long the transformer can ride through the fault. For that purpose, we must follow the standard. So here we don't have any choice. So I, based on the reference, assume for the relay, the fast operation time of the relay number 3 is set by 1 second. So not more than 1 second. Okay, this is the assumption. So since we have this one, the operating time of this, and then considering the PSM, no, considering the selected time deal setting, you can find out the PSM or the operating time of the relay. Okay, the operating time of relay right now is 6 selected, and which is not an important one, but you can check it, double check again. The operating time for that one is considered as 1. Okay, so for that purpose, the PSM, which is, what is the value? It was 1 second. So 1 second and plus PSM must be calculated again by here. So if you have the PSM, you can choose. Okay, assume the operating time for that relay is still 1. is already done. We have to back up relay 4 for this one. Relay 4 is selected in the way to fulfill the current at this relay. So what is the relay fault is 14715. Then we know for the relay 4, which is placed at the other side of transformer, we have to consider the transformer because the fault is by here. We have to consider the transformer effect. So by increasing the voltage, which is 115, of course, the current must decrease. Then the CT1, then the pickup current. So the PSM, or the relay 4, the PSM is selected as 7 point something. Okay, assume 7. Then the operating time is 1 plus, which is 1 here, correct? 1 plus discrimination time. So operating time for this relay is 1.4, okay, second. So let's pick up a time deal setting or time multiplier setting 1.4, which roughly is here, correct? It's okay. Then PSM is 7. It's okay. As you can see, it's already less than. So we can choose the 10. So for this one, the TDS can be selected as 10. Let's go back to the slide. Okay, so this one also is selected as a 10. Setting for the instantaneous element, 1.5 of the fault at this point, fault at here. So fault at here easily can be calculated on this way. Since you have calculated, I'm sure you are familiar with this calculation. Control A, delete everything. Okay, the fault at this point we calculate before. So again, I repeat it. So the I fault is equal short circuit level 950 mega over square 3 times the voltage, which is 915. Okay, the formula is S equal V square 3 VI, correct? This is the formula I used. So the fault current at this point is equal, where did I found it? It's, I think this one, 4769. Yes, 4769 at 115. So let's replace 4769, 1.25. So this is the OPF for this one, means the safety. This is the what we call the fault current, and this is the CT ratio. So PSM, sorry, the setting for instantaneous relay, it reached to 99.36, correct? So since we cannot having, we have to upgrade it as a discrete one. We have to upgrade it to 100. Then PSM, for our case, PSM is this 100 over the pickup current, which is set by 4, and then is 25. Since we know the TDS as a 10 and having the PSM, let's find out the operating time. Is it 0.39? Going up here. TDS equals to 10, and this one is 25. First 25, 20, 25, 30. Okay, so this is 25, correct? Let's have it by number 10. Where is the junction? Zoom in. It's one before last. So we have to increase it. So, okay. I think right now on the So what is the operation time for this relay is less than zero point 0.4, so 0.39 is also acceptable. Okay, so this is same as example you will face in your relay calculation. Sorry about this one. I have to change all of them. Since I share with you this one, I prefer to see which part of this are going to be changed. So this table is not valid anymore for me, and this one is not. Okay, I'm totally opposite of the idea of the book. Directional over current relay. If our system is a ring one, okay, or if we have double-sided of the energy generation, this is one side, this is the other side, so the energy can going from this way to the fault point and the other way to the fault point, correct? So we have to find out the directional current, and we have to set directional and other type of other type of relay. So bidirectional relay, bidirectional relay are the relays who can operate from this way and the other way, left and right, or up and down. And bio, they are bio. But the directional one only focus on the one way of the fault. So if the fault is opposite of, assume the fault is executed by here, okay, on the bus, on this bus, okay. Assume the fault is it's placed at this bus, so the bidirectional relay here will operate because it is going to fed by this one. This load, if it's any current return back, also can operate. I'm not sure about that one related to the load, but mainly I'm going to discuss these two. Okay, this relay will not operate since the direction of the fault is this way. So the only relay must operate is this one. And then the backup for this relay can be considered as this one. So this is the way we considering the directional over current relay. So for this purpose, we can suggest different type of connection, which is 30-degree connection and 90-degree connection. Let's consider this 30-degree. This is 30-degree connection, ATM 0, 30-degree, where the phase of the relay are fed by the phase current. You can see this is phase A, phase B, phase C, and the voltage are VAC, VBA, and VCB. This type of connection is called a 0-degree AMT or 30-degree connection. So let's review. The current of the coil of relay is energized by the phase current and the line voltage, but it's not aligned. Be careful. It's not AB, it's AC. It's very important because usually when we're talking about the three phase is AB, BC, CA. So right now it's not even CA, it's AC. Okay. So the way they energize the relay is totally different. Then he explained based on this figure, this relay provide the maximum torque when the current and voltage are in phase. The condition with present of the connection is satisfied when the system power system factor is square 3 lag. Okay, for the other one, which is called 45, the other way is here. You can see 90-degree or AMT 45-degree. Okay, it's A plus VBC. So whatever VBC it is, you must add 45-degree to that one. Again, VBCA plus 45-degree. And then explain this one. It is good for this connection also ensure adequate voltage polarizing except for three-phase close fault. So if the fault is close to the relay point, if the fault, this is the relay point, correct? If the fault happened close to the relay point, that one cannot be distinguished by the relay. That one close to the relay or very far from the relay are really headache. Always in the power system protection. Parallel transmission line, when we have a parallel transmission line, there is another what we call a circulating of the fault will happen. Assume the fault by here, this is only load and the source only is here. Okay, this is our source. So one of the way the fault can fed is this one, correct? The other way the fall can be in is circulating and coming back. Of course, the rate of IF here is much more bigger than this one. Assume here carry 2 over 3, this one carry 1 over 3 of the fall current, but this one also must be considered for the relay. So because of that, you can thinking about the relay with the direction. So this is bio, and this is only one-way direction over current relays. Here I provide you another example. This example also help you to fulfill your lab 2. Okay, since the network is coming by 5 bus, your network is a 9 bus. When we are going to calculate the and find out the relays. Okay, so for this purpose, you have to consider one time the current, the fault current, and the load current carry from this way to here. Okay, since the A is open, then for the other one, you have to start from this way going, okay, and reach to this point. Assume B is open or switch 8 is open. Okay, for the ring opening at A, when the A is open, start by B. Okay, uh, the short circuit current is given here, and the voltage of all buses given. This is the load at bus L, bus K load, and the other J. Okay, so the B, the total load you can see. Okay, first I'm talking about the loading. Uh, this line, how much load must carry when this switch is open? 7 plus 3 plus 5, the total loading, divided when S is equal square 3 VI, correct? So the current can be calculated, which is this value. For this line, how much current we are going to carry the same? No, since some currents is dropped by here, okay, some loading is dropped, only we have 3 and 5, the load. So the total load is 3 plus 5 is 8 divided by the voltage. Finally, at this point, you can see 5 over that one. And from J, how much load current we have from here to here, since this switch is open, is 0. Okay, so our expectation is to having the same, correct, for the other way, but it's not in that way. Just look, when the number B, when the switch B or 8 is open, 5, 3, 7 is exactly 15. So this value is exactly the same as this one, okay? But the relay numbers are different. Check which relay affected by that one, 1 and 2, correct? This one, 7 and 8. Then when it is delivered here is 5. Here was 7. So 3 plus 7 is 10. So 10 divided by this value is 400 something. Here was because it was 8. You can see. Then which switches affected? Switch 3 and 4 affected. And then in order to, so you can do the other calculation by yourself. It's not a tough one. In order to find out the maximum current for the relay number 1, just look at here. Here relay number 1 maximum current is this value. Here maximum current is 0. So which one is bigger? Of course, it's very clear. Okay. So 650, you can choose 700. Here they choose it 800. Okay. So I think it's the assumption is by here from 100 to 600, you can see this one, then you can jump up one by one, means double. So again, for the B, number 2 is exactly the same. For 3 and 4, 3 and 4 here is 437, here is 200. So 400 is bigger, so I'm going to choose it as a 500 something. And this one can be ongoing. Okay, right now, in order to find out the short circuit, what should we do? In order to find out the short circuit, this short circuit power is given by here, correct? Then again, you have to fulfill what is the short circuit current. So 15 divided by the voltage, this is the short circuit current. And what is the impedance? How we can calculate the impedance? V2 over Z. So this is the impedance. Then we can redraw the circuit in the way in the way the fault at the J. Assume we have a fault at J. Where is J? Where are you? The fault is here. Okay, the fault is here. So we have a source, the source, which is 13.2 divided by square 3. Then we have a fault of this one. We have the impedance of this 150 divided by 13.2. No, oh yeah, 13.2 divided by 150, which is 1.16. 1.16. Then we have 2 ohm, and the other way current is coming is 342. 2 ohm, 347 plus 2, 9. Yes, correct. So 9 is here, 2 is here. So this is the two-way. This is our source. This is our source, and this is 2. This is 9. Both connected to here. This is 2. This is 9. Then you have to make it simplify. 2 parallel with 9, then plus this one divided by this one, and find out the fault current. And then, okay, then divide what is the fault current at here, what is the fault current at here, using the current divider rule. You can see the current divider. And then assume the switch A is open, then assume switch B is open, again find out, and then for the bus K, then for the bus L, the same procedure must be redo. Finally, the worst fault current must be picked by here and set the relay clockwise, and here anti-clockwise. Again, you have to pick the relay, but be careful for the first one, which is close to the source. You have to pick up the biggest value. For your system, I already done this chapter. Okay, these are the exercise. For your unit 9 bus test system, you also have to open one switch. I will give you the instruction for that one. I have to provide you with the data. Since keep the fault at phase. Thank you very much.